In this video, we're going to continue looking at transformations of graphs. We've already seen our parent functions. We've graphed transformations that were horizontal shifts and vertical shifts, and we've looked at reflections of functions where we reflect either over the x-axis or over the y-axis. So in this part 3 video, we're actually going to look at vertical stretching and shrinking and horizontal stretching and shrinking. So we're going to look at an example of applying vertical stretching and shrinking, and we're going to have a function defined by y equals a times f of x, where a is just a numerical value. And we're going to identify at least 3 points on the starting parent graph and then multiply each of those y coordinates by this number a, because that's essentially what we're saying. We have the parent function, and then that's being multiplied by this scalar, okay? So we can label those. The parent function, and then the scalar. Okay, so our first example that we're going to look at is going to deal with a quadratic, x squared, but we can keep this in mind. This is what we're looking for. For vertical shrinking and stretching, if our scalar is greater than 1, then the graph is the graph of the parent function stretched out vertically by a factor of a. If a lives between 0 and 1, so like 0.5 or 2/3, any decimal or fractional value between 0 and 1, then the graph of the parent function is shrunk vertically by a factor of a. So what we're going to be looking for is we're going to be looking for that stretching and shrinking in the vertical direction. I also want to point out that based on these non-inclusive less than or greater than signs, we don't ever look at what happens when a is equal to 1. And that makes sense because if a is equal to 1, 1 times x squared is just equal to x squared, and we would have just our parent function. So our scalar cannot be equal to 1 because then it's not really a scalar. It's not scaling it up or down. It's just the parent function itself. All right, but let's look at our first example. So we're going to think about these functions. We have f of x equals 1/2 x squared. So our parent function here is f of x equals x squared. So we're going to find some values for that one first, and then we're going to multiply those values by 1/2 because that's what we're being asked to do. So let's square each of these. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. For our scaled factor, or scaled function, we're going to multiply each of those by 1/2. 1/2 times 0 is 0. 1/2 times 1 is 1/2. 1/2 times 4 is 2. 1/2 times 9 is 9/2, or I could think of that as 4.5. If you're not a fraction fan, you can write it as a decimal. And 16 times half is 8. Taking half of a number is the same thing as dividing that number by 2, or you can multiply it by 0.5. All right, so let's graph our parent function. Again, I'm going to do that in light gray. So here we go. Let me clear out the lines in the background. 2 would be 4. 3 would be 9, which is off the page, but we'll put it up there. And then this would mirror on the other side. Here we go. So we have that parent function graphed in light gray. Okay, and let's see what happens. So we'll do the new points from the stretched or shrunk version in red. So 0, 0 stayed the same. Then I would have 1, 1/2. So at 1, I would have 1/2. So halfway between 0 and 1 right there. And the same thing would be true for the -1. 2, the point 2, 2 would be on this graph. 3 and 9/2, which is 4.5. So 1, 2, 3, 4.5. And then 4, 8. Right there. So you see how each of these points got shrunk down? And that's because my scalar is between 0 and 1. I'm going to finish this side. So you can see how that parabola shrunk down. Just a little bit, just by half. All right, let's see what happens when we have that same parent function. So we have these values are the same, 0, 1, 4, 9, 16, and they get doubled. So 0 times 2 is still 0. 1 times 2 is 2. 4 times 2 is 8. 9 times 2 is 18. And 16 times 2 is 32. Those got really big really quickly. Again, I'm going to graph our parent function of y equals x squared. And so now I'm going to graph the doubled values. So I have 0, 0. So that point stayed the same. 1, 2. So that's right there, and it mirrors on the other side. 2, 8. So that'd be negative 2, 8 as well. And then the next one is 3, 18, which is way off this chart. Way off this graph. So we can only get those 3 points on this graph. We can represent that we'll touch up there by putting these arrows on the top. But you see how this got stretched up vertically? Each point got vertically stretched upwards. Okay, so that is where we see vertical stretches and shrinks. We are also going to look at horizontal stretches and shrinks. So for horizontal stretching and shrinking, we have something that is going to feel a little counterintuitive, because look at our vertical rules. Our vertical rules told us that if A was greater than 1, then it got stretched vertically. And if it was between 0 and 1, then it got shrunk vertically. And for our horizontal rules, the opposite happens. First off, the scalar is inside the parent function. It is being applied to the x values. Okay, so if A is greater than 1, then the graph of this function is shrunk horizontally. And if A is between 0 and 1, then the graph is stretched horizontally. Okay? And it's by a factor of A each time. So we also want to, so we're going to follow the same process. We're going to identify at least 3 points on the parent graph, on the parent function, and then we divide each coordinate by the number A. Okay? So let's do this. For here, we have our parent function is the square root of x. So what I'm going to go ahead and do is I'm going to write down the values for the square root of each of these x values. That is our parent function. So square root of 0 is 0. Square root of 1 is 1. Square root of 5 is not a pretty number. It's going to give you a decimal number. It's 2 and some change. So I'm going to write the actual decimal value on the side, 2.236. So square root of 6 is 2.449. Okay, and then square root of 7. None of these are nice rational numbers. Only the first two we got were. It's okay. This is 2.645. And it round to 6 right there. So 2.646. So now what we're going to do is we're going to calculate the transform function, the square root of 5 times x. So I'm going to actually write down what that work looks like. Square root of 5 times 1, square root of 5 times 5, square root of 5 times 6, and square root of 5 times 7. So 5 times 0 is 0, so this is going to still be square root of 0, which is 0. This is going to be square root of 5, which again, we don't have the exact number for. It's going to be an approximation, or we can write it as square root of 5. 5 times 5 is 25, so the square root of 25 is equal to 5. And then square root of 30 is not going to be like perfectly accurate. It's going to be a decimal value. And the decimal value rounded would be 5.477. I'm rounding to the thousandths. And then square root of 35 is also going to be another decimal answer. Square root of 35 is 5.916. Okay, so let's graph the parent function, and then we're going to graph the transform function and see what happens. So let's take a look at what's happening. So the parent function I graphed in gray, and right now I'm graphing the transform function in red. And so I want you to understand how this is considered that it shrunk horizontally. Now 0, 0 stayed in the exact same place. But if you look here, where the function was originally at radical 5 or square root of 5, which was 2.236, that got shrunk inwards in the x direction all the way over here when x is equal to 1. And if you think about it, the value of the function at 5 right here on the original graph wouldn't have happened until you were all the way out at 25. So that got shrunk all the way from 25 all the way back to happen at the x value 5. And so we can see that there's that horizontal shrinking going on in that direction. And notice our a value here, a was greater than 1. Okay, so our scalar was greater than 1, and that caused a horizontal shrink because the scalar was inside the parent function, not outside of the parent function. All right, let's see a stretch. I'm going to pause and fill it in and show you. You should pause yourself and try it yourself and then compare. So I filled out the table first. I have my original parent function values, and then these are my transform values. Again, I'm going to graph the parent function in light gray and the new function in red. So I've plotted my points for the transform function in red. I'm going to connect them now, and then we're going to see why this is considered horizontal stretching. So if you think about it, 0, 0, that point stayed the same. It was not affected by the scalar. However, our next point that we can see on both, or are both values of our function that we can see in both the parent function and in the transformed red function, is when the function hits 1. And so in the original parent function, the function hit 1 at 1, 1. In the transformed function, it hits it at 5, 1. So this stretched outwards to the right by that scalar factor. Okay, and so this is why we consider this to be a horizontal stretch, because it's stretching outwards as opposed to stretching in towards the y-axis. And so this is considered a horizontal stretch. All right, I know that this one I think is the most confusing one, so it never hurts to write out the table and test it out. Let's look at this one. Here we're actually given a graph of a function. The graph is below. And what we're asked to do is we're asked to apply this either vertical or horizontal stretch or shrink. So what we're going to do is we're going to look at, is the scalar inside the parent function or outside of it? And that's inside because it's with the x. So the a value is inside, which means we're going to have a horizontal either stretch or shrink. Then we're going to determine if it should be a shrink or a stretch, and that's determined by the rules we saw before. If our a value is greater than 1, then it's going to shrink. So our a value is greater than 1, 4 is greater than 1, and so therefore this is going to shrink horizontally. All right, so let's see what happens. I'm going to go ahead and graph it, and then you compare your answer to mine when you come back. So what ends up happening here is that each of my x values get shrunk in by a factor of 4. So the easiest one to move on this one was this point right here, because I could just divide 4 by 4 and get 1. So this same value of the function should exist now instead of at the x value of 4, should exist at the x value of 1. And so I plotted that point first, and then I just divided each of the x values by 1, or sorry, by 4 to get the rest of the points. They're not very cute. It's a funky scale, but that is what your graph should look like. It should shrink down. All right. This is a summary of all the transformations. I would study it. I would make sure I understood what happens when different things are happening to my functions. Make sure you have your vertical and horizontal shifts down. Make sure you have your vertical stretches and shrinks and your horizontal stretches and shrinks down. And then make sure you understand what happens with reflections, which ones are over your x-axis and which ones over your y-axis. And then lastly is, what order do we do our transformations if we're asked to do multiples? So if we're asked to do multiple transformations, we're going to use the following order. We start with our horizontal shift. So we take our parent function and we shift it horizontally. Then we apply any sort of horizontal or vertical stretch and shrink. Then we do any reflections across the x or y axis. And the last thing we do is our vertical stretch, or sorry, not our vertical stretch, our vertical shift. So let's look at a function and determine what would happen to this function, or to this parent function. So the parent function we have here is our absolute value parent function. Remember, that's the one that looks like the V. Okay. And so let's see what we have going on. Inside the absolute value, x has 1 added to it. So that means, and I have it highlighted in red here, we're going to shift the graph to the left by 1. Okay. Then we have on the outside of the absolute value the number 2. So this is going to be a vertical stretch by a factor of 2. Okay, because remember, for the vertical stretches, it's a stretch if the A is greater than 1. Okay, then lastly, we would then shift the graph down by 3. That's our vertical shift. All right, let's graph it. So I'm going to do the parent function in light gray, and then I'm going to do each of these. I'm going to pause and let you try on your own as well. I've graphed my parent function. I'm now going to do each step, and I'll pause or I'll come back and let you see each step that I've done. So that first step is to shift the graph to the left by 1, which I did in blue. The next thing I'm going to do is do the vertical stretch by 2. I'm going to do that in purple. That just means that each of the y values gets doubled. So let's see what that looks like. You can see in purple now the V got steeper because it was vertically stretched. So each point that I had before got doubled. Okay, so each of the y values got doubled. All right, so the last step is to now shift this purple one down by 3. I will do that in red. So move each point that I have down 1, 2, 3. So that point goes right there. 1, 2, 3. 1, 2, 3. 1, 2, 3. I love the symmetric ones. All right. And we can see, minding my not very straight line on the left, sorry, but we can see our final result here is the function f of x equals 2 times the absolute value x plus 1 minus 3. All right, so that I followed the order that we've talked about. We did the horizontal translation first, then we stretched or shrunk, then there was no reflection in this one, So lastly, we did the vertical translation. So this is an example of how you would do that. Follow it step by step, draw out each of the intermediate steps, and it should work out nicely. All right, if you have any questions, email me and let me know. Thank you so much. Bye.